In part one, I provide the overview, perspectives, and some basic concepts that are involved at the population level. In part two, we will go through some modeling approaches that are pretty popular and generally used at the population level. Before we proceed, I would like to point out that modeling is to some extent like driving. Suppose you want to go from point A to point B. You may have some idea which route you're going to take. However, if you are familiar with the surroundings and you have extra knowledge about some points of interest, that may help you to chart a different route and may better serve the purpose of reaching your destination. Similarly, for modeling, if you want to test some hypothesis, so then you suppose you already know one approach, but if you have a big picture about various modeling methods, that may help you to better serve your ultimate goal. So that's with that in mind, let's start with the concrete modeling approaches. The simplest one at the population level in AFNI is students' Ttest. There are three types. One is the one sample. Right? One sample, I mean, I assume everybody is already familiar with the simple Ttest. So one sample, that means you have one group of subjects, just one effect from subject level. So at each voxel, suppose you have 20 subjects, each subject only has one value. That's the simplest case. So when we build such a model, it's very simple, right? So the model is basically y equals a plus epsilon. So we only have one parameter for the population effect, that's the population average. So if we write in the distribution formulation, then we assume at each voxel, the data from all the subjects follow Gaussian distribution with two parameters, one for the population mean, the other is for the variance. So with those two parameters, we build a model, y equals a plus epsilon, then we solve it, then using ordinary least squares. Then get the population average, estimate the m, the population mean is basically the sample mean. The population variance is the sample variance. So with those two parameters, we have some rough idea at each voxel about the effect of interest. So if we use the 95% quantile interval, that's basically we have the wiggle room around the population mean, so with roughly two standard deviations. So that basically gives us some rough idea about the range or the uncertainty about the population effect. That's usually would be good enough. But in the conventional statistics, people would usually adopt the so-called p-value dichotomization. I'm going to, since that's the popular approach, I'm going to leave as is. The second simplest case is paired Ttest. In this case, we have one group of subjects with two effects of interest. So that's from the data perspective, where each subject will have two values at each voxel. When we build the model, we simply reduce to one sample case by subtracting, by obtaining the contrast between two values. So now we just have one sample case with the two values, the difference between two values, by assuming that they follow Gaussian distribution. So nothing special about that case. Then two sample case, well, that's extension of the one sample case. Now we have two group of subjects. but still each subject will have one effect of interest from the subject level. So this is a special case of a univariate general linear model. I'm going to discuss on the next slide. In case you have missing voxel values, for example, when you align individual subject's brain to the standard space, then especially at the border, then you may have some subjects voxels don't have values. In that case, you can use the option Z skip in 3D Ttest plus plus to handle that case. Suppose you have 20 subjects. There's one subject does not have a value because of the imperfect alignment. One subject at the border of the brain does not have value. So you can use this option. Basically, what it does is only 19 subjects would have values. So when you perform one sample t-test, then you basically, the sample size is 19 instead of 20. So the program will automatically, to handle that case, make an adjustment about the, for example, degrees of freedom and the number of data you have. So that's basically this option does. Next, we're going to cover univariate general linear model. By univariate general linear model, I mean univariate, we mean the response variable, there's only one value. Let's see what exactly that means. So basically, we have one or more groups of subjects. Quantitative variables you may have or you may don't. You may not have. So that depends on the context. So this is generally, sometimes we describe this situation as ANOVA or ANCOVA, right? So if we don't have quantitative variable, we call it ANOVA. If we do, then we call it ANCOVA, because sometimes people call quantitative variables as covariate. But in this case, we don't have any within subject variables. That's why it's called univariate general linear model. If we do have within subject variables, for example, we have within subject factors, then each subject would have multiple values per voxel, right? So that's why in this case, we assume we don't have within subject factors or quantitative variables. So we deal with univariate general linear model. So in terms of data structure, each subject just have one value per voxel. Then we build this model, we assume the data follow Gaussian distribution. So the population mean would be the intercept plus, depends on the situation, we may have multiple parameters. Then plus the variance for the residual term. So the effective interest would be those population level parameters, intercept, slopes, right? So you have multiple groups. We can also consider those multiple groups. We can parameterize those multiple groups as quantitative variables by dummy coding them. So then we can treat them as the group comparisons as slope effects. We do have quantitative variable. In that case, the tricky thing is centering. Usually, it's not covered in statistics textbooks because it's considered trivial from modern perspective, but practically it is crucial and may have some impact on the result interpretation. So you have to be very careful. If you're only interested in the slope effect, in that case, you don't have to center a quantitative variable. But for other effects, centering becomes crucial and may result different results and different interpretations. So that's a subtle issue. So in general, I would pretty much recommend you center quantitative variables all the time. Because even if you're not interested in, the slope effects, but centering may help to achieve numerical stability. So that's another gain thanks to centering. Another issue when we deal with a quantitative variable is we need to make assumption. The typical one is about linearity, right? So that's additive effects. Whether that's valid or not, I mean, it's difficult to say, especially when we deal with brain image data, because with the massively univariate approach, it's difficult to deal with, because if it's just one voxel, we can try different models with hundreds of thousands of voxels. I mean, the data model validation is pretty difficult to handle. So the crucial thing is linearity assumption is valid, or is that too strong? That's difficult to say. How to handle that? I mean, if it's violated, we don't even know, right? So model validation and visualization are with your image data is just so tricky. So later on, we'll discuss a generic approach to handle nonlinearity. So univariate general linear model basically can be considered an extension to a two-sample t-test, as we mentioned on the previous slide, right? Because two-sample t-test is a situation we have two groups of subjects. So those two groups, we can dummy code the two groups as a quantitative variable, right? So in that case, the group comparison becomes a slope, right? ANCOVA is also a special case of a univariate general linear model, right? So especially when we don't have within subject variables, basically everything is between subjects. So you can be groups or can be a quantitative variable, but that quantitative variable is also between subject in the sense that each subject has only one value for that for each quantitative variable. So in AFNI, we have two programs available for univariate general linear model. One is 3D Test++, the other one is 3D MVM. 3D Test++ is basically we have one or two groups, plus you may have one or more between subject quantitative variables. 3D MVM is more generic. Basically, it handles ANOVA and COVA, and also when you have quantitative variables between subject quantitative variables, not within. So basically, 3D MVM is more generic than 3D Test++. Multivariate general linear model. Why is multivariate? Well, in this case, we usually have one or more group of subjects. So that means it's an extension of parity test, because parity test, each subject have two conditions. So that can be considered as a within subject factor. That factor has two levels, right? So automatically, parity test is a special case of ANOVA with a factor of two levels. But more generally, multivariate general linear model deal with a case we have within subject factors, right? So then we may also have quantitative variables, but those quantitative variables are between, not within. So that's the limitation with the multivariate general linear model. But if we do, it's not a multivariate general linear model anymore. You would use linear mixed effects model approach to handle that scenario. So in this case, each subject have multiple values per voxel. Why multiple? Because we have at least one within subject factor, right? So each factor has multiple levels. That means each voxel will have multiple values per subject. So the model is a little bit different in the sense each subject have multiple values. So it would be a matrix at the left-hand side. So we have basically we can write the model equation as a design matrix x times the coefficient vector. Then the residual is not a single parameter anymore. I mean the variance. It's a variance covariance matrix. This approach is definitely better than univariate approach because it can correctly handle within subject factors. In neuroimaging, the popular approach seems to be a univariate generative model. Seems people use that to handle the case with within subject factors. That can be problematic because the hierarchical structure, when we have within subject factors, it's a little bit tricky, delicate to handle. Mostly it's in neuroimaging. If we use univariate generative model approach to handle the case with within subject factors, most of the time it's troubling and the results are not necessarily correct. The problem has been pointed out several times in the past, probably 10 or 15 years, but the case is still remains uncorrected. So again, whenever you have a quantitative variable, then you need to take care of the centering issue and also be mindful of the underlying assumption, the linearity assumption. Whether that's a probability or not, that's difficult to validate and difficult to visualize. But there is an alternative which we'll cover later on in Party 3 during the advanced modeling approach section. Multivariate generative model includes student Ttest and the univariate generative model as a special case. So the program in AFNI is 3D MVM, and also you can use 3D ME and 3D RMER to handle because it's also a special case of a linear mixed effects model. So in the output, as you probably know, it's basically a ANOVA and COVA. So the traditional statistical framework provides the omnibus test that covers main effects and interactions. Suppose you have a factor with 3 levels. So the main effect is inferred by the omnibus F-test, basically to indicate whether there are differences across all the 3 levels. So it gives you some overall idea about the differences across the levels, but it's not precise in the sense. You still don't know where the differences are, right? Suppose you have 3 levels A, B, C. The difference can be between A and B, A and C, or B and C. You don't know, it can be all of them or could be some of them, right? So the F-test just gives us that general assessment. So usually we have to resort to specific T-tests to partition that omnibus test. So the F-test is useful in the sense it provides that overall assessment, but usually we cannot stop there. We have to go a little bit further. That's the effect partition part. Some people call it post-hoc testing. So you basically obtain those contrast tests, right? So A, B, C, you want to get A versus B, A versus C, and B versus C. So, or you may also want to know each individual level, right? A, B, C, you want to know A, B, C, because their magnitude can help you to interpret each of the contrasts. Again, the programs in AFNI are the basic one is 3D MVM. For multivariate generative model, that one is good enough. But the other two, the linear mixed effects modeling for is just more generic. It's probably better suited for complex cases, which we'll discuss right now. So the data structure, when we adopt the linear mixed effects modeling, is when we have at least one within subject variable. That within subject variable is can be factor or can be a quantitative variable, right? So multivariate generally model would be a special case of linear mixed effects modeling. Under this framework, we have this notion of fixed versus random effects. During part one, we already discussed briefly about the differentiation between the two types of effects. Fixed, under the traditional studies framework, are those parameters in the model that we consider as they're fixed in sense. We're interested in them. They are usually at the highest level, population level in the context of FMI. So for example, the factors or the experimental variables like groups, tasks, and slope effects, I mean, for quantitative variables, those effects usually we are interested in. Even if we're not interested in, they are at the population level. So we consider they are fixed, right? So it's basically the conditional statistic. We have this hypothetical idea about basically when we will perform population level modeling. The reason we do that, we want to generalize from the specific subjects which we recruited for scanning to a hypothetical pool or hypothetical population. So for that generalization to be valid, we have to have this concept of random effects. The random effects basically is the lower level, such as subjects, trials, or families, depends on your experiment design. So those lower level variables, we're not interested in them. That's why we recruit those subjects. Those subjects are, randomly drawn from the population on campus. They are random in the sense that they are incorporated into the model as dummy variables, right? So they are, and we make a assumption about their distribution. Typically, it's Gaussian distribution. Pretty much all the time. That's the prior distribution. So in the end, we don't talk about their specific effects. We don't say subject A has a higher effect than the group average. Subject B is lower. We don't say anything. That's because the reason we recruit those subjects, we treat them as representatives. So in the end, it's the population effects that we pay attention to, we generalize to. We want to say something about the population effects. So in terms of the data, we need to we have this hierarchical structure, right? So we have population level, then we have subject level, then within, under each subject, we have this, in this case, we have within subject factors or quantitative variables. So for example, we have a factor within subject factor A, B, C, 3 levels. So each subject underneath each subject have that layer. So we have, in this case, we have 3 levels: population, subject, then tasks. So 3 levels. We have this specific hierarchical structure or multi-level structure. So that's the reason we adopted this linear mixed effects form. We can handle the complex hierarchical structures. So we may have cross subject effects, within subject effects, or when we have families, then family is one level, then within each family we have family members. Right? So then we may have a cross random effects. For example, when we have a subject and the task level, then under each task we have trials. So we may have crossed random effects, for one for subjects, the other one for trials. So the formulation is as opposed to the univariate or multivariate general linear model, we have 2 design matrices, one for fixed effects, the other one for random effects. That's why in the distribution formula, we have this X for fixed effects, X design matrix. The Z design matrix for random effects. So we solve this. The solving part is also a little bit different and more complex and time consuming. Usually we use we strict maximum likelihood approach to solve it, iteratively to solve it. So when we have a quantitative variable again, you need to pay attention to centering. In the programs like 3D-MEE or 3D-MER, there's an option to how to delicately handle the centering part. And also, you need to keep in mind the underlying assumption is linearity. Usually, you would use 3D-MEE to handle situations like you have a quantitative variable within subject quantitative variable, like in a longitudinal study. Suppose you want to use age as an experimental variable because it's a longitudinal study that it lasts for several years. The age is a variable, but it's within subject variable because each subject has multiple age, right? Suppose each year you scan the subject once, so 5 years you're going to have five values for that variable. The second case that the linear mixed effect model approach is very useful to handle missing data. Okay, so as long as the subject, this is the whole brain level, not like the 3 Ttest plus or case where you have missing only at the voxel level. This is at the whole subject level. Suppose subject did not show up at one particular task among 3 tasks. It's a within subject factor with 3 levels, 3 tasks. Suppose one subject did not show up for one particular task. In that case, the traditional ANOVA approach will not be able to handle the scenario, but 3D-MEE would be able to handle it as long as you think that that subject did not show up for some wonderful reasons, not because of the task is too tough for that subject. And also, we use this approach to handle some complex random effects, like you have more than one random effects, like subjects, trials, or you might have a cross structure, like an intersubject correlation for lateral scanning. Sometimes people use linear mixed effect model to get intra-cross correlation. That's for test. We test reliability, which we'll talk about during the advanced section. Special cases like Parity Test within subject and ANOVA and COVA are special cases of a linear mixed effects model. Even though linear mixed effects model is considered as advanced modeling approach, well, it has been available for decades, but in FMI, it's still considered as an advanced complex approach. It does have a few limitations. For example, usually we have to assume data follow Gaussian distribution. That can be problematic because sometimes data have outliers. All data is skewed, right? It's not symmetric. So Gaussian distribution can be a problem. Another problem with the linear mixed film and also the traditional statistical framework in general is point estimates, because they provide the parameter estimates as a point. It's not considered as a distribution, especially for variances. With linear mixed effects model, we can only get an estimate. There's no uncertainty associated with the variance estimate. That can be problematic when we deal with tested reliability, right? Because we kind of get some sense of uncertainty. Another problem with the traditional framework is measurement error. The input is usually we assume there's no sampling error, but with FMI data, the beta values from individual subject level, they are not the right measurement. They carry some uncertainty because they come from a regression model. They're estimated. Whenever we have estimated, there's an uncertainty associated with it. That's a standard error embedded in the denominator of the t statistic. So, but unfortunately, we can't take advantage of that with the linear mixed effects model. So basically, the y value we assume it's precise. There's no uncertainty, right? So that's the assumption. So that's a third limitation. Lastly, there are probably more, but here we talk about these three. The number 4 is the model can fail in the sense the numerical solvers can have some convergence issue, or when the parameter hits the boundary, the algorithm may just gets trapped there, cannot get out of it, then would fail to find the optimum values. So that can be a problem for linear mixed effects model. So the next slide, I can talk about the uncertainty, which we just discussed. When we deal with the population level analysis, when the beta values from individual subject, that we use that as input, as y for population level models. But those y values, they're not precise. They do carry some uncertainty. That uncertainty is basically the standard deviation. So that uncertainty is ideally we need to use that extra information to perform a more robust population analysis. That the way typically we can achieve a better modeling accuracy is to use those T statistic, because the T statistic contains the standard deviation of each beta values from the subject level. We can use the uncertainty, the standard deviation, as a weighting mechanism. So suppose one subject has a relatively reliable beta value. Reliable means their standard deviation is relatively small, right? Relatively precise. So at the population level, we should treat that subject as, put a higher weight for that, or assign a higher weight for that subject. Will have a more to say, have a more proportion, more weight for that subject. In contrast, another subject is unreliable in the sense the beta value is unreliable with a large standard deviation. So we should put a lower weight for that subject. So with that rating mechanism, we get a weighted average for the population effect. So that's the basic idea. With that weighting, we usually achieve higher accuracy and inferences at the population level. But how to incorporate that uncertain information at the population level? The program in AFNI is called 3D MIMA. MIMA stands for Mixed Effects Multi-Level Modeling Approach. Multi-level, in this case, we incorporate the individual subject levels information, especially the reliability information, into the group model. So that's the multi-level part. So the input, in this case, we would require beta value and the T statistic from each subject. But in terms of modeling capability, it's pretty much similar to 3D Ttest++ in the sense that we can deal with one group of subjects or two groups of subjects or paired case, right? One group of subjects with two conditions. Similarly, we can also deal with missing data at the voxel level. Suppose a group of subjects, some subjects don't have values at some voxels, especially like at the border of the brain. So you can use the option missing data with 0, because suppose a voxel value is 0, we consider that as missing, because typically when you have the beta values from individual subject regression model, you will not get 0 beta values regardless the strength of the effect, right? So you can get small beta values, but you will not get 0, exactly 0. So you get 0, that's because of masking. You provide a mask out. So that's why we can use the 0 values as the signal for missing data. Another modeling perspective, approach at the population is to handle, to want to single out the quantitative variables. Those quantitative variables at the population level, usually the typical ones like age, reaction time, brain volumes. Sometimes people even treat between subject group factors like groups as a quantitative variable, because by dummy code them, we can also treat them as a quantitative variables. But generally, when we have have quantitative variables, we need to be aware the distinction between subject versus within subject quantitative variables, because that distinction would have impact as to which modeling approach and how to handle that. Also, when we have quantitative variables, we need to be, especially when we have longitudinal versus cross-sectional, that's also a little bit tricky. Like, for example, age. In longitudinal study, age would be a within subject quantitative variable. In that case, either mixed effects modeling would be the way to go. Again, whenever have quantitative variables, linearity is the default assumption. It's popular and easy to manage, right? So that's also easy to interpret as well. So the programs to deal with quantitative variables are those three. Pretty much everything most of the programs like 3Ttest++, 3D MIMA, 3D MVM, 3D ME, 3D MER. When we have within subject quantitative variables, are only limited to two, 3D ME and 3D MER. How about the nonlinearity? That's something advanced. Traditionally, people would use polynomials to fit nonlinearity. Typical ones like with quadratic or cubic, right? So that's basically an extended version of linear model. You just, when we have x as a quantitative variable, then we'll add, for example, quadratic relation, we use x squared, right? So we can treat that as two variables. One is x, the other one is x squared. Those now we just convert to a linear model with two quantitative variables. But the problem with the polynomials, especially for neuroimage data, is because we deal with hundreds of thousands of voxels, difficult to choose what the order of the polynomials. We can't examine at the voxel level, we cannot visualize them. So it's difficult to judge the fitness of the model, right? So maybe some brain regions, linear would be good enough. Some regions, maybe you need a quadratic or even cubic. We don't know. We just blindly, select order. Usually quadratic or cubic maybe to handle it. So it's difficult to validate the bot approach and also to visualize it. Better approach is to choose an adaptive approach that can select the nonlinearity based on the data, use the data to guide, to teach us about the nonlinearity. That approach is way much more flexible. That's a little bit advanced. That approach is called smoothing splines. It's similar to the concept of using tens or cubic spines at the individual level to model the hemodynamic response function. So at the population level, we have a similar approach. That approach is called a multi-level smoothing splines. The program is 3D MS. It's freshly available now. You can use to check the documentation in the help to find out the usage. There's a paper associated with this program, so the underlying theory is covered in that paper. I think lastly in part 2 is about hemodynamic response modeling. The typical approach in AFNI, we use a fixed shape curve to fit the hemodynamic response. This approach is very popular. Pretty much everybody uses it because it's simple, straightforward, at both subject and the population level. We just use curve to fit all conditions, all subjects, all groups. Or that I mean, it's in simple. We don't need to worry about, right? In the case, I mean, in the end, each condition will have one beta, especially at the population level. That's pretty straightforward. But the problem is it's not flexible, right? So it may hurt the sensitivity, I mean, statistical power. And I mean, suppose to do conditions, they may have different shape. The peak of the hemodynamic response, they may have different shifted between the two conditions. If you use same curve, then you may lose the sensitivity to detect the subtle difference between the conditions. So ideally, we would adopt a more adaptive approach. Instead of fix the shape, we use an adaptive curve. Well, it's pretty much like a smoothing spline case. We use multiple basis functions. That's like multiple rulers to put in the different locations at the time axis to find out the hemodynamic response. So in the end, each condition, we have multiple betas to characterize the hemodynamic response. So that the relative magnitude of those betas would trace out the hemodynamic response curve, the shape. So we would use multiple betas, suppose, for example, 10 betas to describe the hemodynamic response shape. So the subtlety and the complexity at the population level is how do we handle that response curve? That's a little bit tricky, but definitely we do have two options to handle it. The old approach is basically we treat that multiple betas as a factor, as a within subject factor, right? So at the group level, we just have extra factor to handle it. Then we have that program we have extra factor within subject factor. Then 3D MVM would be able to handle it. So if there's an example in the help, and also there's a paper published in 2017 that describes the details, the underlying mechanism about this modern approach. Now we have a new approach. Presumably it's more robust, better than the previous approach. We use the multi-level smoothing spline to characterize the response curve. This approach is still testing and under development, but the basic idea is available now and can be used for general use